Hello, welcome to UGC EPG Pathshala in the course of linguistics. I'm Somnath Roy. I'll be speaking on speech signal processing. The course module has been written by Dr. Samudra Vijaya K. So I'll be speaking on behalf of him. The overview of this course module is introduction. We'll see how human beings used to talk using speech as a medium, and how human apparatus like human speech production system works in producing different kind of sounds, and followed by speech signal analysis in time and frequency domain, and then followed by speech signal processing, and finally we'll look at the topics of what kind of features are essential for modeling, building an ASR system or speaker recognition system. So as we all know that human beings, the primary mode of communication between human beings are the speech. Even if we are at a distance, we can talk to each other via phones, and the mode of communication is speech. So human beings use speech, which is an acoustic signal, to exchange the thoughts encoded in that speech signal, and get exchanged to the follow listeners or the interlocutor. So the primary goal of speech communication is to convey an idea in speaker's mind, or the idea or concept or information that is encoded in the speech signal. So a speech signal also carries auxiliary information such as the speaker's characteristics, the language being used, as well as the acoustic environment. So if you look at the topic of, look at the schematic diagram of an ASR system. So in ASR system, the speech signal goes as an input and the text comes as an output. So even the human ear, or the whole cognitive system, takes speech signal as the primary input, and then we decode that speech signal and find the linguistic encoded meaning from those speech signal. So how is the speech production system of human beings behave, and how it works to produce different kind of sounds through which we exchange our ideas. So different sounds in human beings is produced using different type of articulatory configurations. So we will look at the pictures to see how what kind of articulatory configuration is required to produce different kind of sounds. And in particular, we'll look at the voice sounds, because voice sounds are produced by the vibration of vocal cords or vocal folds. And the rate of vibration of vocal fold is known as fundamental frequency. The perceptual correlate of fundamental frequency is called pitch. So just to have a look at this fundamental frequency or speech production system, I will just show you some of the images which relates to the schematic diagram of speech production system of human beings. As you can see in this figure, that the vocal this is the vocal cord, and the vibration of this vocal cord, what happens, like when these two vocal cords come close to each other, they vibrate, and there is a pressure difference between subglottal and supraglottal. So this subglottal pressures, when it increases the supraglottal pressure, then air releases between these vocal cords, and that release of air goes to the oral tract or oral tract, and there different kind of configuration generates different kind of sounds. So the main articulators are the lips, the tongue body, jaws, and another is the nasal cavity as well as velum, as you can see. So the main source of voice sounds are are the vibration of vocal cords that you can see, and the complete details of this articulatory mechanism can be found in as has been cited in Pandey 2015 in this UGC module. So and what happens is, once the air through that vocal cord is released, that small air pocket coming through the glottis causes resonant vibration in the air molecule in the vocal cavity, and that resonance causes some sort of energy that get concentrated in some particular frequency bands in that resonant area, and that sort of energy concentration in different frequency bands are called Formant frequencies. So what we have you can also observe is that the distinction between vowels can be measured on the basis of Formant frequency, or the energy concentration at different frequency bands. So generally the Formant frequencies are nothing but the energy concentration at higher frequency ranges. So next we'll look at this. Now we'll see the speech analysis in time and frequency domain. So in time domain, the time is once the speech signal is recorded, you can see that speech waveform, and the speech waveform is represented as time on the linear horizontal axis, and amplitude on the vertical axis. So and in looking at the waveform, you can see the region where the energy is more. So in this example waveform, you can see this is a sentence with the word called Thiruvananthapuram, where it has 5 vowels and 8 consonants, and you can see all the energy, the region where higher energies are concentrated are the vowels. So this is not pretty conventional to look at the waveform and to detect what kind of vowel it is. So to analyze this feature, which feature can disambiguate or categorize what kind of vowel it is. So to analyze that, we have to move into different domain that is called frequency domain. So now we are changing the domain. We are moving from time domain to frequency domain. So in this domain, you will have to take small frame of or small chunk of a sound, and from that you have to analyze the frequency spectrum. So frequency spectrum is nothing but a representation where frequency will be on the horizontal axis, and the amplitude in decibel will be on the vertical axis. So one point I just want everybody to note down is that amplitude is a logarithmic in dB is a logarithmic scale, because this it is not because a human ear is designed in such a fashion that it is linear at some scale to some frequencies, and then it starts behaving non-linearly. So the difference between the minimum and the maximum is so high that it is very difficult to represent that on the linear scale. That's why we use logarithmic scale to represent this amplitude. So the amplitude that we see on the vertical axis is on the logarithmic scale. So and we have also seen that the frequency component can be is capable of distinguishing what kind of vowel it is. So if we have to distinguish between a, e and different vowels, then we have to plot their frequency spectrum to categorize those vowels, and from those frequency spectrum we calculate the formant frequency, the peak of the formant, and the width of the formant, and the frequency range. So this frequency range, peak and width, is used as a feature to categorize the vowels. So generally, two types of peaks are visible in spectrum. One is called narrow peak that occur at regular frequency level, and another is broad peak, which is irregularly spaced peaks in spectral envelope. So what we do is to get that broad curve is we just join the curve to the top of the narrow peaks. So we do not need the narrow peaks to categorize the vowels. We just need the broad peaks, and that broad peaks are capable to distinguish the different type of vowels. So and now we'll be moving to different feature that we use for building different ASR system and different speaker recognition system. Capsule analysis is capstrum. Capstrum is one of the important features that is used in speech that is extracted from the speech signal to build a speech or speech recognition system or a speaker recognition system. In this capsule analysis, what we do is we take small signal, let's say of 25 milliseconds. So that will go to the FFT module. So FFT module will calculate the FFT of that short time signal, and then we compute the log. So that log of FFT will be the power spectrum, and then we get the log spectrum, and when the log spectrum is computed, then we compute the inverse Fourier transform. So inverse Fourier transform of log spectrum is called capstrum. So the smoothing of log power of spectrum is called capstral smoothing. So we just need the capstral coefficients to represent a short signal. So if we have a short signal of 25 milliseconds, so we can extract certain number of coefficients from the capstrum to say that okay, these many capstrum coefficient can represent this signal. So the capstral coefficients are one of the important features that is used for building ASR and some such systems. So as I have already pointed out that our human auditory system behaves linearly to some frequency, and then it becomes nonlinear. So to map that phenomena in speech modeling, we use a scale that is called MEL scale, and MEL scale is generally defined as, if we have to use MEL scale, so the formula for MEL scale is 1125, this means 1125 multiplied by natural log of 1 plus f divided by 700. So if we have to compute the MEL scale or MEL scale of a frequency component, then we have to apply this formula to get the MFCC feature or MEL scale frequency, MEL capstrum. So we have looked at the feature called MFCC, but one of the important feature is spectrogram, which phoneticians use for visualizing a phone. So and spectrogram can be extracted using small speech files or small speech frames, or we say short duration speech signal, and then compute the log FFT square, and the output will be your spectrogram. So spectrogram is one of the simplest and elegant feature for characterizing a phone, and most of the phoneticians use these features. So as we have seen that MFCC is it's very difficult to extract the spectrogram spectral features from spectrogram if the environment is noisy. Yeah, so if we have to compute the MFCC of a waveform, then what we do is we take a short time signal, which is represented here by xn, which passes through the FFT module, which gives an output as power spectrum. Then power spectrum is goes as an input to MEL filter, and that MEL filter output goes to we apply the log on the MEL filter output, and we get log of MEL filter output, and followed by we take the inverse Fourier transform, which is nothing but the MFCC. So MFCC is one of the important feature for speech and signal processing things. So if we have if we have to build a speech recognition system, we use MFCC as one of the features to build an ASR system. So now we have to see temporal variations in speech spectrum. Okay, so this is I guess we'll be covering in next module. So next is, yes, so next what we have seen till this time in this module is how speech production system happens, how voice sound can be produced in human speech production systems, and how it is how voice acts as, or how speech acts as a primary medium of communication even when vision is not there. Okay, even if we are at far distance. And then we have seen what is actually the time domain signal and the frequency domain signal, how in frequency domain we can use their features such as formant frequency as well as formant width and peak to categorize different kind of bubbles. So in next lecture we'll see how these features can be leveraged to build a speech recognition system or speaker recognition system. Thank you.